Over 80% of individuals post-stroke experience trouble walking, typically presenting with hemiparetic gait. This gait is characterized as slow, asymmetric, and inefficient. Specifically, a major contributor to impaired locomotion is decreased ankle function. Over the past 4 years, our lab has developed multiple exosuits to assist the paretic ankle. The first prototype was a tethered exosuit with an off-board actuator. We demonstrated this exosuit can improve ground clearance and forward propulsion symmetry while also reducing the metabolic cost of walking with respect to the suit powered off. However, its tethered design limited mobility, constraining its use to treadmill and short overground walks. These lab-based studies served as important input into the design requirements of an autonomous version. The updated design allowed a wider range of activities from walking outside to standard clinical tests. The autonomous version provided further benefits to gait symmetry, forward propulsion, and toe clearance. Still further input from clinical partners, study participants, and laboratory data identified additional improvements for the exosuit. The latest exosuit was optimized in its weight and volume, and redesigned control schemes match or exceed previous benefits to the wearer's gait, while reducing electrical power consumption. The exosuit consists of 6 key components: an actuator and waist belt, cables customizable to the wearer, a calf wrap with integrated sensors, a battery pack, an insole, and a pair of foot-mounted IMUs, one on either shoe. IMUs located on the shoe detect foot orientation relative to the world. First, we detect non-paretic toe-off. We apply a small amount of actuation to pre-tension the cable, readying the suit to deliver mechanical power. By mid-swing on the non-paretic side, we are actively assisting paretic propulsion. The gait detection algorithm then detects paretic foot lift. By this point, plantarflexion assistance is complete. The plantarflexion cable goes slack to allow for dorsiflexion assistance. Shortly after the paretic foot contacts the ground, the non-paretic foot once again lifts. The step-by-step controller collects information from the previous stride, makes adjustments to position commands, and the cycle repeats. This strategy leads to a control algorithm that is responsive to a wide variety of gait types and robust to different gait speeds. To validate our exosuit design, we conducted testing with 3 post-stroke participants walking unconstrained over ground. These clips show the typical effect of walking with the exosuit turned on. Observed results match or slightly exceeded those from previous exosuit designs, while requiring dramatically lower power consumption. In particular, 3 out of 3 participants saw an increase in forward propulsion, and 2 out of 3 participants saw an increase in toe clearance. Future work will involve performing studies to better understand the biomechanical and physiological effects of wearing the device.